Hello everyone. So this is our next chapter, which is laws of motion, the most short chapter in our mechanics, because here we will answer what is the cause of the motion that we have been discussing for so long. So we discussed the objects moving from one place to another place or one position to another position. To be very to use technical terms, we say that it moves from one position to another position. That's a displacement. It moves with constant speed or it moves with constant velocity, and it moves with an acceleration. We discussed all these aspects of the motion, but we never spoke about what is causing this motion. So that what in all this is answered in this particular chapter, and that is why this chapter is very important when you speak about mechanics. So what is causing the motion? The answer is simple: the force is causing the motion, right? Force is something that causes the motion. But is that the only job that the force does? No, force causes so many other jobs as well. So it can cause a motion, or it can move a stationary object. That is one thing that it can do. It can move a stationary object. Suppose this duster is stationary right now. If I want to move it, I should apply a force. So if I want to move it up, or if I want to move it rightward or leftward, I will have to apply force, right? How was I applying the force? I was applying the force using my hand. So an external agency can cause a motion of a stationary object. An external agency can cause a motion of a stationary object. That is first job the force can do. The second job that the force can do is it can stop a moving object. So this is the second job it can do. If an object is already moving, you take some box, put it on the floor and kick it. It will start moving. Now if your friend wants to stop that box from motion, he has to put his leg in between and stop it. So his leg will apply that force when that box or that ball is moving on the floor. So force can stop a moving object. That is the second job it can do. The third job that the force can do is it can set an object in rotation. You hold a ball in your hand, or you hold a marker in your hand, you hold a pen or anything that you want to hold in hand, you hold it and try to rotate it. So is it moving forward? No. Is it moving upward? No. Right? But is it at rest? We cannot call that, we cannot say that it is at rest. It is moving, but it is rotating. So force can cause this rotational motion also. Another job that the force can do is it can cause deformation. That is change in the shape of the object. Now I don't have any object who's in here whose shape I can change and show it to you, but you have so many objects lying around you, right? You take a small wooden stick and bend it, its shape changes. You take your eraser, you try to bend it, its shape changes. You take a plastic bottle, crumble it, its shape changes. So these are so many things that force can do, and they are included under deformation. So these are different functions that a force can do. It can cause the motion, I mean it can change the translational motion of the object. Either it can cause the object moving, or it can stop the object that is moving. Then it can also set the object in rotation, and it can deform the object. These are the three primary functions that a force can do. Okay, but what happens to this force? Is it in picture when an object is moving with constant speed or constant velocity? Is the force in picture? Is the force really in picture there? For example, so in fact that question has been a very important question for so many years. Especially Aristotle faced this dilemma whether the force can really, if is it really necessary for causing a motion of a uniformly moving object. For example, you take a bow and arrow and shot the arrow with the help of the bow. Now the arrow is moving with constant speed ahead. Does it do that? No, it slows down and finally falls down, right? Now arrow was supposed to continue its constant speed motion, but it didn't, right? So why did it slow down? Aristotle couldn't answer that. He felt that since the arrow is moving forward, then the air around it must be pushing the arrow forward, which now we know that it is not true. We know that the arrow slows down because of the air resistance. So air is actually not supporting the arrow to move, but it in fact is trying to stop the arrow from motion. But that was not realized in somewhere around 400 BC, somewhere around 384 BC. Aristotle, in this period, he felt that a force is necessary for a constant speed motion of an object. So if you kick a ball on the floor, for it to move with a constant speed, there must be somebody or something that is continuously pushing the object forward. Then only it can continue the forward motion, is what Aristotle felt, which now we know not to be true. He concluded this from a common experience. He looked at the objects that are around him and he felt that no objects continue their constant velocity motion. If you kick a ball, it slows down. If you shot an arrow with a bow, it slows down. So everything is slowing down. That means for them to continue in constant motion, an external force must be necessary. Then came Galileo. So what did Galileo do? He did this one experiment. He arranged two plane surfaces in this fashion, kept a small ball over this surface. He arranged them in such a way that they are inclined at the same angle and made the surfaces very smooth, and this object also was circular. So there was very little friction that was involved. Then he released the object from here. The object went down and climbed up almost up to the same height as it was when the angle theta was same. So it almost covered the same length over the another plank. Then what he did was he could change the angle of this plank. So he reduced the angle further and further. So the plank was very long. He kept reducing its angle, and every time he found that this object, when it comes down and then climbs up the plank, it more or less covers the same height. Okay, it more or less covers the same height. Now for it to cover the same height, it has to travel more and more and more and more length, right? If it wants to go to the same height, it has to cover so much of length. Now if I go on doing this, if I go on making this plank at lesser and lesser angle with the ground, ultimately one situation will come when this object will fall, it will come down, and then the second plank will almost be horizontal. So the object will keep moving over it without application of any force. That is how Aristotle, that is how Galileo concluded that no force is necessary for the motion, constant speed motion or constant velocity motion of an object. What did he conclude? No force is necessary for an object to move with constant velocity. If an object wants to move with constant velocity, it can move on its own. You don't need to apply any force to it. But if you want to stop it, then you will have to apply a force. The property by virtue of which an object continues its state of motion. So basically, if an object is moving with constant velocity, this plank will give some velocity to the object as it comes down, and then it will move with constant velocity over the other plank, and it will not stop unless you try to stop it. So the object has this property by virtue of which it will continue, it will maintain its constant motion. That property was defined as inertia. So inertia, you can define it as property by virtue of which a body possesses a tendency to continue its state of motion. Suppose a body is at rest, it will want to be at rest. Suppose a body is in motion, it will want to be in motion. If you want to stop a moving body, you will have to apply force. If you want to move a body that is already at rest, you will have to apply a force. But the body on its own, it will have a tendency to maintain its motion, called as inertia. Now you find this inertia at many examples in our day-to-day life. when you if you have a chair around you which is at rest, if you want to push it, you will have to apply some force. But that force, when you want to apply the force needed in the beginning is large. Suppose a chair is a metal chair, or suppose you have a cupboard in here. You want to move the cupboard. The force that is necessary to move it, to start its motion is large. Why? Because the cupboard has a tendency to be at rest. So the force that is necessary to change its state of motion, which is at rest, now you want to change it into moving object. The force needed will be large. Once it starts moving, you will have to apply very less amount of force just to overcome the friction at the legs. The rest, the cupboard will continue on its own. Whatever force is necessary, it is necessary only to overcome the friction that is offered. Friction is basically the resistance offered by the floor onto the cupboard. Suppose your friend is running, you want to stop him, you will have to apply large force in the opposite direction. You are standing in a bus and suddenly bus driver takes a turn. You feel as if you are being pushed outward. That is your inertia. Because you had a tendency to move in a straight direction along with the bus took turn, but you still have that tendency to move in a forward direction. So you get pushed outward from the bus. You feel as if you are being pushed outward from the bus. These are all tendencies of inertia. The driver suddenly presses the brake. You move forward, right? You tend to move forward because you had a tendency to move forward. The driver applied brake, the bus stopped, but your body still has a tendency to move forward on account of this inertia, and that is why you tend to move forward. Or if you are standing in a bus which is stationary and suddenly the driver starts the bus, you feel a jerk backward, right? That's because of a tendency of the inertia. So day to day life we see so many examples where the inertia plays its role, and that was coined as a law of inertia by Galileo, that every body has a tendency to maintain its motion, maintain its state of motion, which is either at rest or in motion. So it will maintain on its own. No extra force is necessary for it to maintain its position or its state of motion. That was coined by Galileo. Now what did Newton do? Newton used Galileo's ideas. He tried to modify those ideas and make them suitable for the context of our motion, and he coined his first law of motion. What is Newton's first law of motion? The law says every body continues in its state of rest. So first law by Newton, every body continues in its state of rest. What is state of rest? State of rest is stationary. So every body will continue its stationary position or of uniform motion. If the body is in uniform motion, it will continue to be in uniform motion. If it is at rest, it will continue to be at rest. So every body, when I say every body, it is applicable to any body in the universe. So it is applicable to solids, liquids, gases, any state of matter, the law is applicable. So every body continues in its state of rest or of uniform motion unless it is acted upon by external unbalanced force. See, every word in the law is very important. So every body, that means it is applicable to any state of matter. You take a solid or liquid or a gas, continues in its state of rest or of uniform motion. So the law covers both the cases. When the body is at rest or in uniform motion, it will continue what it is doing. Till what time will it continue? Unless, important, till what time will it continue? Unless it is acted upon by an external unbalanced force. That means it will continue its state of rest or of uniform motion until you apply some external unbalanced force. All the three words are necessary. So if you apply external, and as long as you don't apply any external unbalanced force, the body will continue its state of rest or of uniform motion. Now what are these three important words? External. The force has to be external to the body. That means the forces that are internal to the body cannot move it. Take a simple example. You are sitting in your school bus. The bus is stationary. The driver is, he's not starting the bus very soon, but you want to go to the home as early as possible. So what can you do? Can you do this? You go and start pressing against the windshield, the front windshield of the driver side. So you alone cannot push the car. So probably your friends join you. 50 of your friends, all of you all are inside the bus, and from within the bus, you are trying to push it from the front windshield. What at max can happen is the windshield will break, but the bus won't move even an inch, right? Why? Because the force that you are trying to apply is from within the bus. It is not an external force. So if you really want to move the bus, what should you do? You all 50 should get down, go to the behind of bus, and then start pushing it from behind. Then you become an external entity to the bus. You are no longer inside the body, you are outside the bus, you are outside that body, and then you start pushing the bus will move, the bus may move. It depends on how much force you collectively, you 50 can apply. But if you can apply enough force, the bus will start moving forward. But only thing is, you have to be an external agency to the bus. So only external forces can cause motion or can stop motion. Remember this, only external forces. The second thing is unbalanced. 50 of you get down, 25 start pushing from behind, 25 start pushing from the front. You know that joke we always tell. 4 people get down and they start pushing the car, but it still doesn't move. Why? Because 2 are pushing from the front, 2 are pushing from the back. So some kind of situation, 25 people, 25 students pushing from behind, 25 pushing from the front. The bus won't move at all because it becomes a balanced force. So the force has to be external, the force has to be unbalanced to cause a motion. And yeah, so external unbalanced force, that has to be there. Then only the state of rest or of uniform motion of the body can change. This is what Newton's first law can tell us. You take many examples. A raindrop probably moving from the clouds. It has 2 forces acting on it. One is the force of air resistance, and the second one is force of gravity, mg downward. That means gravity pulling it towards the earth, and this is air resistance force. After some distance, these both forces get balanced with each other. We'll actually see the numbers and we'll actually go into the proper numerical after some couple of lectures. But right now we just consider that this raindrop is acted upon by these 2 forces, and then it starts moving with a constant velocity, which you have seen in the last lecture, which is 10 meters per second. So the raindrop keeps moving with same velocity because earth is pulling it down, air is pushing it up. So the forces get balanced and the raindrop moves with constant velocity, right? So the things can move with constant velocity if the forces are balanced. That is what in fact take away from our first law, that things stay at rest or they move with constant velocity if the forces on them are balanced. So things staying at rest when the forces are balanced is called as equilibrium situation. For example, this duster, is it moving now? No, it's not moving. Why? Is there no force acting on the duster? There are several forces acting on the duster. One is forced by my hand, which is upward. I am trying to stop the duster from falling down, so the force is upward. The weight of the duster, which is trying to pull it towards the earth, but still the duster is at its own place because the forces, though they are external, but they are balanced. Hand is applying a force on the duster, that becomes an external force. Earth is applying force on the duster, that becomes an external force, but they are balanced, so the duster won't move. So if you want to cause a motion or if you want to stop a moving object, you have to apply external unbalanced force. Okay, so that's a takeaway from our Newton's first law. Now in the next lecture, we will be seeing Newton's second law, and we will see some more terminologies related with the Newton's second law. We will see a couple of numericals, interesting numericals. So we will slowly move ahead in this chapter. We will see second law, then we will see third law and the applications of this law, and then the terms of acceleration, circular motion, and so many other terminologies which we have seen in the first and second chapter, they will get clearer. Okay, thank you.